everybody, it's Miss PG from your WCA physics class, and today we are going to be looking at some kinetic and potential energy problems as a bit of a supplemental. I'm going to walk you through some of the practice problems in the text and looking at the work-energy theorem. Kind of solve some of those problems that way. Hopefully they will make a bit more sense after we walk through them. So, I'm going to share my notebook with you. Let's go ahead and put it to full screen real quick. And bend it down so that you guys can see my notebook. And we'll flip it around. There you go. You get a nice view of the notebook there. Maybe zoom in a little bit so you can get full screen. And we're going to talk a bit about problem number 1 here. And this is actually using sample problem C on page 167 of your text. So, sample problem C. Page 167 of your text. Sample problem C states that on a frozen pond, a person kicks a 10-kilogram sled, giving it an initial speed of 2.2 meters per second. How far does the sled move if the coefficient of friction between the sled and the ice is 0.1? Okay, so it's giving us some information to start with, and we'll go ahead and look at that. It tells us that the mass of the sled is 10 kilograms. Tells us that the initial velocity of the sled is 2.2 meters per second. Because the question is asking how far does the sled go, we know that we're looking to figure out how far it goes until it stops. So then our final velocity would be 0 meters per second. Gives us the coefficient of friction, u, is 0.1. And what it asks us, it says, is how far does the sled move? So what we're looking for here is d distance. So one of the things you have to realize here, again, is that work and energy are kind of two sides of the same coin. So the work-energy theorem says that the net amount of work done, W net, is equal to the change in kinetic energy, delta KE. And we have different formulas for each one of these. So work is force times distance times cosine theta. So I'm just going to put that over here. Work is force times distance times cosine theta. And I know we want to know distance, so this is also the way in which we're going to be able to solve for distance. As you can see up here, we don't have force given to us. However, according to Newton's second law, force is equal to mass times acceleration. And we're looking at the force of the sled, which is basically its weight, which would mean that the force is equal to the mass times the pull of gravity, gravitational acceleration. So we know that force here is actually mass times small g. We know that small g is negative 9.81 meters per second squared. So I can substitute mg here for that f and come up with my work is equal to mg d cosine theta. And don't forget, we have to add mu to the front of this, because mu is going to be affecting how much force basically is, how much the friction is going to affect that force. Okay, so we're adding mu to the front. That's that coefficient notation. So we have what our net work equals. And we also know that net work equals the change in kinetic energy. Well, kinetic energy, delta KE, would be the final kinetic energy minus the initial kinetic energy. That would be delta KE. Right? Now, kinetic energy is energy of motion. So if the sled is in motion, it has kinetic energy, but as soon as it stops, it doesn't. So we know that our final kinetic energy has to be 0 because it's not going to be moving. So essentially, the kinetic energy of the system is equal to the opposite of the initial kinetic energy. Formula for kinetic energy is 1/2 mass times velocity squared. So if I do this, that's going to give me kinetic energy. And I know, according to this, that this equals this now. So I'm going to set this here equal to, actually I'm going to probably get a second page here just for the camera. I'm going to set my net work, which was UMG d cosine theta equal to the negative 1/2 mv squared. Okay, so then I'm going to use this formula to solve for D. So solving for D, to isolate D, I'm going to divide both sides by UMG and cosine theta. So negative 1/2 mv squared divided by mu mg cosine theta. Your mass will cancel top and bottom, so you don't need to worry about that. So we can rewrite this a second time. I can actually move this 2 if I want down below as well. Instead of having a fraction in the numerator, I can just call that 2 in the denominator. So then that would give me D equals negative V squared over 2 mu g cosine theta. Okay. Now, if you think about it, you're pulling a sled, or the sled is actually not being pulled, but it's sliding horizontally. So it's got an angle of 180 degrees. Okay, so it's sliding horizontally. So we're going to change the theta to 180 degrees. So we have our knowns up here, right? Stick those up on the top here. We have velocity is 2.2 meters per second, so negative 2.2 meters per second. Square it. And then we have 2 times 0.1 times negative 9.81 meters per second squared. This was actually negative before. I forgot to bring the negative down here before. Times cosine 180. Oh no, I'm sorry. That negative sign does not need to be here. We kept it up on top, I forgot. what ends up happening is that cosine of 180 is negative 1. So this bottom number will be negative. Okay. So when we do the math at the top here, negative 2.2 squared and at the bottom, you're going to have 2 times 0.1 times negative 9.81 times negative 1. So the negatives cancel each other out. You have 1.962. And that's meters per second squared. Okay. And this one is meters squared per second squared. So divide those two. 4.84 divided by 1.96, and you get a total of 2.47 or 2.5. The meter squared, one of the meters will cancel. Second squareds cancel, so we end up with just meters as our final units, and that's the correct units that we would need for this one. So this shows us the distance the sled would travel would be 2.5 meters. Okay? So again, I hope that makes sense to you. You can always go back and rewatch this, but we're going back to this work-energy theorem, that the net work is equal to the total change in kinetic energy. So this is very important to be able to solve these some of these kinetic energy problems. If you have questions or concerns, feel free to give me a call at extension 2204. Otherwise, have a fabulous day.